We move perfectly on time to next talk. And I see Professor Kerry Rowe, that he's already here, but I have a surprise. We have a special guest today, Dr. Daniele Cazzuffi. I asked him to please turn on his webcam. Daniele Cazzuffi, he's the past president of the International Geosynthetics Society. So I would like to leave the floor to him to introduce the lecture by Kerry Rowe, the 11th Mercer lecture. Please.
Thank you very much, Marco. Ladies and gentlemen, it's a real pleasure for me to introduce the next lecturer. That means Professor Kerry Rowe, a very good friend since, unfortunately, many years.
Yes.
I remind you that in the previous Iacmag conference held always in Torino in 2005, I had the honor to introduce his ranking lecture on the long-term performance of a contaminant barrier system that was held a few months before in London. And today, I have this real privilege to introduce his Mercer lecture on another subject that is geosynthetics for construction on soft foundation soil, another subject in which Kerry is an outstanding worldwide expert. And exactly on this subject, on embankment on very soft soil, Kerry presented an invited lecture only 32 years ago in Bologna on the occasion of our third Italian conference on geosynthetics. And I still have the volume of these important proceedings in my library. And I am sure that also Kerry will play an important role in the next international conference on geosynthetics that will be held in Roma 1 year after the next Iacmag conference, so exactly from 17 to 21 of September 2023. So Kerry, now the floor is yours. We are all excited to follow your Mercer lecture.
So thank you very much, Daniele, for a lovely introduction. It's good to see you again. Looking forward very much to seeing you in person, if not beforehand in Rome. So ladies and gentlemen, it's my pleasure and privilege to give a, albeit shortened version of the Mercer lecture here today, which is sponsored jointly by the International Geosynthetics Society and ISSMGE, as well as Tensar International. Ladies and gentlemen, over the next 30 minutes or so, what I would like to do is share with you 40 years of exploration of the use of geosynthetics to aid construction of embankments on soft or difficult soils using numerical analysis. My topics start fairly simply and then build up in complexity with the objective of leading to the final topic, highlighting current challenges related to pile-supported embankments and the need for current researchers to pay more attention to the lessons from the past 40 years that I will be presenting to you. So let us begin where I began 40 years ago, building embankments over fibrous peat. For those of you not familiar with fibrous peat, it's a highly organic soil where you can still see the organic structure. But it can be described as a soil by a Moore-Coulomb equation with a cohesion intercept that arises from the tensile strength of the reinforcement or the fibers that are reinforcement, and a frictional component with a typical friction angle of 26 or 27 degrees. Now, of course, to get that friction, we need an effective stress, and the submerged unit weight of peat is very low. And so if we want to construct on it, we need to control the pore pressures. and that's represented by B bar here, which is a ratio of the excess pore pressures to the change in total stress, giving rise to those excess pore pressures. So we wanted to build an embankment, and this was the first that I'm aware of, over 7 meters of fibrous peat with a very high water content and voids ratio. And we wanted to achieve somewhere around 1 to 1.5 meters above grade. And we built several instrumented sections, but the one I have time to talk about was with a reinforcement of multi-filament geotextile. Properties are given on the slide, but the most significant one is the break strain of 25%. So because we need to allow pore pressure to dissipate, we build in a number of stages. And in the first stage, we placed 2.74 meters of fill. And at the end of the fill placement, we had 2.6 meters of settlement. And the strain in the reinforcement was about 5%. And you can see here the predicted and observed deformations. Now, we left it for 8 months, and at the beginning of the next construction season, our 2.74 meters of fill had given rise to 3.1 meters of settlement, which means, of course, that the center of the road was now below the original ground level, which was the water table, as you can see in this photograph. Now, during that time, the pore pressure dissipated and the soil gained strength. And as the soil gained strength, the reinforcement became less critical and the strain reduced. At this point, it's 2%. We then added more fill. So by the end of stage 2, we had 5.4 meters of fill, which gave 4.2 meters of settlement. And our strain in the reinforcement is now 11.5%, so roughly half of its failure strain. We come back 2 years later, and our 5.9 meters of fill has now given 4.8 meters of settle, but we are 1.1 meters above original grade, which was the lower end, but we've reached our objective. And our strain has dropped from 11.5% to 8%. Now, the important point here is that we're on a traditional soil, which gains strength as the pore pressures dissipate. The reinforcement becomes less important with time. The strains are reducing. So what are some of the important lessons here? The high modulus geotextile reduced lateral movements and increased stability. But what it doesn't do is it does not prevent large consolidation settlements. If you're going to get large consolidation settlements without reinforcement, you will still get them with reinforcement. There was, as intended, significant pore pressure dissipation during construction with a maximum B bar of 0.34. And from a numerical perspective, the important thing here was that the effective deformation and strength parameters combined with pore pressures provided good agreement between calculated and observed behavior with a relatively simple more Coulomb failure envelope. Now, using calibrated numerical model, using field cases such as this and others I have not time to talk about, we developed design charts for use in practice. And this is one example only. So that if you wanted to build an embankment to a height h above original ground level, and it has a unit weight gamma, you multiply the two together, say 20 times 1.5 meters gives 30 kilopascals. And if our peat was only 3 meters deep, we would hardly need any reinforcement at all. But if it's 5 meters deep, we now need 400 kilonewtons per meter in stiffness. And if it's 8 meters deep, we need 800 kilonewtons per meter in stiffness. So we see that stiffness of the reinforcement is an important consideration. Yes, strength's important, but so too is stiffness. Now, this is for the simplest case of a firm base below the peat, but similar charts have been developed with soft soil below the peat and have been successfully used for over 35 years. So let's move from peat, where we have a dissipation of pore pressures during construction, to undrained construction on soft clays. And we're now moving to a test embankment in the Netherlands. And here we have an organic clay, and it was excavated to form a trench. And that clay from the trench was used to form a retaining bank. Then hydraulic fill was placed until failure occurred. And it occurred at a fill height of about 1.75 meters. And you see here a photograph after the failure occurred. There was also a section where reinforcement was used. Very similar section. And in this particular case, the reinforcement was placed on the organic clay. The excavated clay was used to form the retaining bank on top of it. The reinforcement was a multi-filament woven polyester with relatively high stiffness, about 2,000 kilonewtons per meter, relatively high strength, and a failure strain of about 10%. With the placement of hydraulic fill, failure eventually occurred at a height of 2.75 meters, or empirically we see about a 60% increase in the height due to the reinforcement. Now, if we look at this numerically, the analysis of the unreinforced is very simple. It can be done by finite elements, by limit equilibrium, you get the same answer. A failure height of around 1.8 meter with a circular failure passing tangent to the firm base and through the toe of the trench. What is more interesting is to look at the reinforced case. And here we see at 1.8 meters, when the unreinforced embankment failed, we have contained plasticity. So the reinforcement is carrying some of the load and reducing transfer stress to the soil. But eventually, at 2.05 meters, we have uncontained plasticity. And all that's holding the embankment together is the reinforcement. Now let's examine this from the point of view of strain at a critical point in the reinforcement on the inside edge of the retaining bank at point A. And we're plotting here the increase in strain in reinforcement versus embankment fill height. And the observed values are shown as circles and the finite element calculations as a white line. And you can see that for the first 1 meter of fill, there's virtually no strain in the reinforcement because the elastic is, they're sort of behaving elastically. It's carrying the load itself and it doesn't need the reinforcement. But as we go over 1 meter, the soil starts to develop plasticity and the plastic region grows, the reinforcement has to work harder. And by the time we reach a height of 2.05 meters, we have uncontained plasticity. And the reinforcement is what is holding the system together. Now, it happens that this also corresponds to the working height based on a factor of safety of 1.3. And you can see that at this working height, the strain in the reinforcement is only about 1%. And we often find that the reinforcement is primarily there to give you your factor of safety on these conventional soils. Now, if we load it past that point, the soil isn't going to take it anymore, and so the reinforcement strains increase fairly quickly until failure occurred. And in this case, failure occurred at a strain of 3.3%. That's only a third of the strain the reinforcement can carry. So why did it fail? And the answer is lack of anchorage, pull out of the reinforcement between the organic clay in the foundation and in the retaining bank. So we not only have to think about the strength and stiffness of the reinforcement, we also have to think about pull-out mechanisms. So up to this point in time, we've looked at clay where we could construct to a desired height using basal reinforcement under undrained conditions. But often we want to go higher than that. And so we need, just as we did with peat, to allow pore pressures to dissipate during construction. And one very effective way of doing that is with prefabricated vertical drains. Pvds, as we know them, have been around for decades, have worked very effectively on their own in soil improvement. But what I would like to talk about today is the use of Pvds with reinforcement. So here we have a situation where we've got a set of Pvds at 2 meter spacings. We're going to use a construction rate of 2 meters per month. And we're going to plot the net height, which we define as the fill thickness minus the maximum settlement versus the embankment fill thickness. And we can see that without reinforcement, we can construct to about 2 meters. Then we get failure. If we put in reinforcement with a stiffness of 250 kilonewtons per meter, in this particular example, we don't see much improvement. But if we increase it to 500, we get to about 3 meters net height. At 1,000, we get to about 4 meters net height. And at 2,000, we get to 6 meters net height. But during this, of course, we're getting consolidation. And just as we saw with the peat, the reinforcement is not going to prevent consolidation settlements. If you get large consolidation without reinforcement, you'll get large consolidation with reinforcement. What the reinforcement does is it reduces the plastic deformations, the undrained deformations. So to this point, I have been dealing with traditional soil mechanics. I've been dealing with soils who experience a decrease in pore pressures after we stop placing fill. And therefore, the effective stress increases and the strength increases. Now we're going to make a life a little bit more complicated. We're going to do what I call rate-sensitive soils. Now, you could argue with me, and you'd be right, that all clays are rate sensitive. But I'm talking about a special case, and that is rate sensitive clays where the pore pressures don't dissipate after we stop placing the fill. In fact, they continue to increase after we stop placing the fill. In a survey of embankments in Canada by Crooks et al., they found that 35% of the embankments, a little over a third, fell into this category. And it occurs in many parts of Canada and other parts of the world. Now, in New Brunswick, to the east of Canada, they've had the embarrassing problem of building roads, thinking they'd done their job very nicely, and then months to years later, the road collapses because it's on rate-sensitive soil. And so we had the opportunity to build a number of test embankments, only one of which I have time to talk about today, and that's the reinforced one. And it was built on the soil whose properties are described here. I don't have time to go into them, but I do draw your attention to the Liquidity Index, which between 1 and 6 meters was about 1, which meant that the natural water content of the soil was close to the liquid limit. And as a consequence, this is often a good clue that we may have a rate-sensitive soil in the context I'm talking about it. Now, we built an unreinforced and a reinforced embankment. And the reinforced, again, had polyester geotextile with about 13% failure strain and a stiffness of 1,500 kilonewtons per meter. And we successfully built it to 8.2 meters and then waited. And then after a period of time, you can see our monitoring location that's at the toe of the embankment moved up 2 meters because failure occurred after the end of construction. This was a viscous type failure, and it was due to creep of the foundation soil. The deformations and excess pore pressures increased after the end of construction, and a failure occurred at what we call the critical time, which is when the pore pressures had increased sufficiently that the combination of the strength of the soil and the strength of the reinforcement were not enough to maintain stability, and failure occurred. Traditionally, these designs are done with field vein data, and even with the typical correction, such as the Beerham correction, they overestimate the strength. The good news was that reinforcement did increase the failure height and reduce viscoplastic deformations. But now let's explore what are the implications of these time-dependent characteristics of the foundation for the reinforcement. So we're going to take exactly the same properties that we had at the Sackville embankment and design an embankment with a traditional limit equilibrium calculation using a factor of safety of 1.3, the vein shear strength with correction, and a allowable strain in the reinforcement of 5%. So it's designed assuming the reinforcement force is mobilized at 5% strain. And we can see here in this numerical plot of the largest reinforcement strain against time that at 500 hours, we've reached our 5% strain. Now, at the end of construction, we're at 6% strain. Well, that's not too bad. If this were a traditional soil, we would then expect the strains to decrease as the soil gains strength. But here, we have a very different situation. We have a situation where the soil is losing strength because of ongoing buildup in pore pressures. Now, for this type of reinforcement, the failure strain can be between about 11.5% and 13%. So depending on when it reaches its strength limit, the failure would occur 12 to 21 days after the end of construction, consistent with what we saw at Sackville. If this reinforcement did have the capacity to go beyond 16% strain with the same stiffness, then we would have had a stable embankment. So I've now illustrated to you that life becomes more complicated when we have these rate-sensitive clays that I'm discussing. Up to this point, all my reinforcement has been polyester, which has the beauty that it behaves pretty much elastically. Very nice. Unfortunately, this is not true of all reinforcement. Some of them experience viscous behavior. So now let's explore both a rate-sensitive soil and rate-sensitive reinforcement. So we're again going to plot net fill height, which is thickness minus maximum settlement, but this time against the long-term reinforcement strain that's permitted. And we're going to begin with a polypropylene geogrid and construction at 10 meters per month. And if our allowable strain was 3%, we could safely build to 2.9 meters in this particular case. If it was 5%, we could build to 3 meters, about 5% increase. Now, if we were to change the rate of construction, but keep the same reinforcement, We reduce the rate of construction to 1 meter per month. We change the time-dependent pore pressure situation in the soil. And so now, if we allowed 3% strain, we get a 7% increase in embankment height to 3.1 meters. What if we change the reinforcement? So we keep the same construction rate at 10 meters per month, but we now use a polyethylene geogrid, which is less rate sensitive. And at 5% allowable strain, we see a 12% increase in embankment height. So what this illustrates to you is that with embankments with basal reinforcement, we need to consider, is the soil rate sensitive? Is the reinforcement rate sensitive? Because both are important. So now I'm moving to the last segment, which is a very hot topic today. You pick up most of the journals that deal with the behavior of geosynthetic reinforced soil, and you're pretty sure every issue will have a paper about column-supported embankments. And we're going to work our way very quickly through these, starting with the simplest. So we're going to start with columns that are floating and either have or don't have a layer of reinforcement over the columns. Then there's a load transfer platform, which is a granular material, and then the embankment itself. And there was some nice field work that was done, and I'm also looking here at the analysis of that data. And the first case we're going to discuss, there was no reinforcement. There were the columns, but no reinforcement. And the pilehead settlement was 10 millimeters. The settlement halfway between the columns was 130 millimeters, giving a differential settlement of 120 millimeters, which, depending on the thickness of the fill, would be reflected at the surface to some extent. Now, if we put in the reinforcement, we see the pilehead settlement increases to 30 millimeters. It's doing more work. The subsoil reduces to below 80 millimeters, and the differential settlement is less than 50 millimeters, or less than half what it was before. So the interaction between the pile and the reinforcement is going to reduce the differential settlement. Well, that's all well and good, but we may also want to be using prefabricated vertical drains. So now we're getting ourselves into a really three-dimensional problem. We have a series of deep mix columns. We have a series of Pvds. Obviously, this is not drawn to scale. And we're going to analyze a three-dimensional section. And we're going to be interested, if we had more time, at both points A and B between the columns. But because we are limited in time, we're going to focus our attention on just settlement at point B and leave pore pressures for another day. So here we are plotting the maximum crest settlement versus time. And we see in yellow the results we would get without prefabricated vertical drains. So we have, in this particular case, a settlement of about 0.6 of a meter, and it would take us about 7 years for the primary consolidation to be complete. If we put in the Pvds, then we see a better situation. We get a settlement that's 30% less. 30% less because we've reduced the undrained deformations, the plastic deformations, because of pore pressure dissipation. And we find ourselves at essentially complete primary consolidation within about a year. Now let's introduce viscosity of the reinforcement. So we have here a plot of tensile strain in the reinforcement versus time. And we have results shown in blue for elastic reinforcement and in white for our polypropylene geogrid we looked at before. And we have selected them to have the same stiffness at the end of construction. And you can see as a result of the time-dependent properties of the reinforcement, we've got about 1% more creep after a decade. So 1% more strain due to creep. But at exactly the same time, if we look at forces, we see that the elastic force is greatest, and we are probably about 10 to 15 kilonewtons less in terms of the force in the reinforcement. So we have simultaneously got creep and relaxation occurring in our reinforcement, which we need to consider. So all of this is to bring us to our very last point, end-bearing column-supported embankments. They are not well understood. There are many design methods that are lacking. As we saw before, we're dealing with a load transfer mechanism. We have load transfer from the soil to the reinforcement to the pile. But also what's going on here is arching. Arching in the load transfer platform and potentially in the embankment soil above it. So now we've added an additional complexity to its overall behavior, soil arching. And as Atard Sagi pointed out a long, long time ago, it is a particularly universal phenomenon. And we need to consider it. So what's the problem with existing models? They tend to assume a shape of the failure surface with soil arching, which is okay, except that those assumed failure surfaces tend to lack a sound theoretical basis. Often they're empirically based, and while they give a good description for the conditions for which they are developed, they're being applied too generally. Now, what's the complexity with soil arching? Well, it is complex because it involves strain softening, and it involves a level of arching that depends on the amount of reinforcement sag. And you can get good agreement between observed behavior and predictions from even modestly simple models if strain compatibility is achieved. Unfortunately, that is not often the case. And if we are trying to build a system that has good serviceability-based design for these problems, we must consider time-dependent, coupled arching stress reinforcement deformation behavior. That is quite a mouthful. That, in fact, pulls together everything we've been talking about and adds arching. We need to consider how long it will take to reach working conditions. Current limit equilibrium models that are often used are deformation and time independent. Yes, they are useful. They're useful for ultimate limit state designs, but they cannot be used for analysis of serviceability. Also, short-term performance is not a good guide to serviceability assessment, because in many of these situations, we have to pay attention to longer-term deformations due to soft soil creep and reinforcement creep and relaxation. So this brings me to the end of my story. I'd just like you to bear with me for a minute or two while I give 3 conclusions. I'd like to leave you with 3 points. Firstly, soil reinforcement is well established as a cost-effective alternative to or augmentation of traditional construction methods. Second, understanding the performance of the reinforcement and its characteristics is critical to success. But while geosynthetics are very useful, they're not magical. They obey physical laws. And as with all engineering materials, we need to design properly. Thirdly, while geosynthetic properties and characteristics are indeed important, we mustn't get so absorbed in the geosynthetics that we forget the soil mechanics. It too is an essential consideration for ensuring good long-term performance. And when you put all of these things together that we've discussed today, we have today's current challenge in reinforced soil. And with that, I would like to conclude and thank you for your attention.
Thank you very much, Professor Kerry Rowe. It is time for interact with the speaker. If anyone wants to pop up and say a few words, we have a couple of minutes before the coffee break. And Kerry, I would like to ask you an additional word on. I mean, in your talk, of course, you have highlighted some aspects that are related to the topic of the conference, challenges and innovation. So I would like you to tell us another few words on this path. So there are many youngers connected today, and what are the challenges and innovations in the field of geosynthetics? So where should we look at for the next, I don't know, 10, 15 years? You mentioned limits of existing models for soil arching, for example. You said we have to understand geosynthetic properties. So where should we go?
Well, I think there are many aspects to the answer to that question. If I just stick with where I was today, the challenge that I'm highlighting for you is that we really need to bring together a lot of the concepts that have been developed over many years to solve just the apparently simple problem of pile-supported embankments with reinforcement. And that will require a lot of developments and modern three-dimensional, highly sophisticated numerical analysis. And progress is being made, but I think it's going to keep PhD students working for at least another half decade to a decade before they've solved that problem completely. And as we talk about these things, I've talked about a number of geosynthetics. Geosynthetics don't stand still. They're evolving. New materials are being developed all the time. And just in reinforcing materials, new materials are being developed, and we need to understand their characteristics and how to model them. But more broadly, as Daniele alluded to, I also do a lot of work in the environmental field. And there are many growing challenges for us as a society. Climate change is inducing major challenges for us. I do work in the Arctic and the Antarctic. Actually ties in very nicely to our first talk on sea ice. And there are many geotechnical challenges arising from the melting of permafrost, the changing of flow conditions, the use of geosynthetics is in its infancy in these very cold climates, and how there is an interaction between changing foundation conditions, say due to melting permafrost, how there's a change in the performance of geosynthetics under these cold conditions that get cold and then warm up and get cold. There are many challenges there, both from a purely geotechnical perspective and from a geosynthetics perspective. And from what I like to do is bring the two together. So those, I can keep going on, but that's a couple of examples.
There are a number of queries that came out, so I would like to if you can stay with us another more minute.
Yeah, sure.
So thank you for giving ideas on where to go. There is a query directly on your talk, and it says, does the arching occur also for floating column supported embankment?
Yes, but to a lesser extent.
Yeah, and
it depends a bit on exactly the column design. The more rigid the columns, the more the arching will be significant. The issues that I raised will be significant. But yes, you'll get arching even with them.
There is another comment by Luger Suarez Burgoa, and I don't know if he wants to turn on his microphone or if the director can turn his microphone on, but I can read what he wrote. I want to congratulate with Professor Rowe for his interesting lecture about fibrous peat here in Colombia. So he's connected from South America. It must be very early in the morning for you. We deal with those organic clays. These are deep as lengths of meters inclusively, and they are most of the time saturated. Are geosynthetic the unique solution to deal with these soils? So he asked if geosynthetic is the unique solution for this.
Oh, I would be very careful about saying anything was a unique solution. I think they're a very good solution, but again, you have to design appropriately and you have to understand what they can do and what they can't do. I've tried to make the emphasis because a lot of people have had the misconception that it would be useful for reducing consolidation, and it doesn't. What it does do, it reduces plastic deformations. It allows you to put more fill on during stage construction. But if you have a highly organic soil, you're still going to need to be very careful with your pore pressures, and reinforcement is a benefit, but it's not in and of itself a solution. It's part of a solution.
Good, thank you very much. Now, well, I think we have to stop because we passed the time. It's time for the coffee break, but before the coffee break, we have, I would like to leave the floor to Julia Prodan, that I see she's here now. She's from the Technical University of Cluj-Napoca in Romania. And why is she here? Well, because now we want to announce the winners of the EPIC. We had this, you might remember that we had this contest dedicated to the young girls, let's say, and Julia kindly accepted to be the chair of the evaluation committee. So I leave the floor to her.
Hello, everyone. Many thanks, Marco, for your kind introduction. It's a pleasure to be part of the conference and of the warming up event, which I think was an amazing idea, especially in these times that we are all experiencing. Hopefully, like you mentioned at the beginning, we are starting to see the light at the end of the tunnel, and next year we will celebrate together in Torino. So while I was preparing the slides for presenting the awards for the Promising Investigator Contest, I came across this quote by Franklin Roosevelt that says, "We cannot always build the future for our youth, but we can build our youth for the future." And I thought it represents quite well the concept that we had together behind this competition, which is to support and promote young, talented and successful young researchers and give them the opportunity to present their work, and of course further on be themselves an inspiration for other young engineers and researchers that follow this path of research in our interesting yet difficult field of geomechanics. So just a second. Okay, so of course we had some eligibility criteria in our competition. Not so many, quite easy and logical, I would say, which was to have a single author of the papers, and the authors should be promising young researchers at age of 35 and under. And there are two awards within our competition, our young competition, which is of course the EPIC winner, that will have the opportunity to present the paper during a plenary session within the conference, receive an invitation to the social dinner, and be waived of the conference registration fee. And the second type of award, which is the EPIC nominations, that will have the opportunity to present the paper during the parallel session, receive an invitation to social dinner, and be waived of 50% of the conference fee. So, of course, we did receive several papers, and I would like to take this opportunity to thank all the participants for their contribution, for their interest in the competition. Together with the evaluation committee, we and of course through the review process, we have selected our awardees. And my colleagues, the winners are, and I will start with the EPIC nominations. And I also have a surprise here, because we have what we said and called as a triple tie, and the winners are. So we have Dr. Matteo Oriem-Ciantia, I apologize for any pronunciation mistakes, from the University of Dundee, with the paper Micromechanics of Pile Cyclic Response in Sand. We have Dr. Federica Genovese from University of Messina with the paper entitled Influence of Soil Nonlinear Behavior on the Selection of Input Motion for Dynamic Geotechnical Analysis. And Dr. Maria Lianapoli from Politecnico di Torino with the paper 3D Slope Stability Analysis of a Complex Formation with a Blocking Matrix Fabric. So congratulations to the winners of the EPIC Nominations Award. And I would like to invite them. They are here with us. So dear, maybe we can start with Maria. Maria, if you want to say a few words, the floor is yours.
Yes, good morning to everyone, and thank you very much for this award, for selecting me to receive this award. And my paper is part of the research I carried out during my PhD, and focuses on 3D stability analysis of slopes in geotechnically complex formations characterized by a blocking matrix internal arrangement. And where there is still much work, much research to do on this topic. And this award gives me more duties to improve my work. So thank you again very much. Thank you to both the evaluation and the organizing committee.
We have postponed the conference so you can continue on the work, and next year you can present some updates.
Of course.
Maybe, yes, I hope so. Thank you.
Unfortunately, we do not have too much time, like Marco mentioned a few minutes ago. So thank you very much, Maria, and congratulations again. I would like to thank you. I would like to move on to Federica.
Thank you. Good afternoon. I'm really grateful to the evaluation committee of the Promising Young Investigator Contest and to the organizing committee of the Iacmag conference for this important nomination. It's a great pleasure that my paper about the it's a great pleasure for me that my paper about the influence of soil nonlinear behavior on the selection of input motion for nonlinear dynamic analysis has received this important recognition. I'm sure that this nomination will be a great incentive to improve even more my research activity. In addition, I want to say many thanks to my research group of the University of Messina that has supported me since the first day of my PhD. I hope to meet all of you in presence the next year in Turin in 2022 conference. Thank you and goodbye.
Thank you so much, Federica. Congratulations again. Matteo?
Yes, can you hear me?
Yes, Matteo, hello and congratulations.
Well, thank you very much. Thank you for the panel, and I would like to congratulate also the other nominees and the winner that I'm very keen to discover. I think I peeked and I've seen him already, but I don't want to be the spoiler here. But yeah, I mean, you can read the paper. I will not present it here, but basically it's using the discrete element method to study cyclic response of piles in crushable soil. Very proud and honored for being a nominee for this prize. And I'm actually seeing that, I mean, we didn't do it on purpose. I think that the committee didn't, but I see 3 Italian names here, and I'm very proud also about this. Yes, and I will certainly celebrate with family today from our home working positions. Thank you very much.
Okay. Thank you, Matteo, so much. Okay, so my dear friends, let me introduce to you the EPIC winner. That is Dr. Alessandro Rottaloria from Northwestern University with the paper Analytical Modeling of Energy Geostructures. Alessandro, congratulations. The floor is yours.
Thank you very much, Julia, and good morning, afternoon, and evening to everyone. I would like to take advantage of this occasion to thankfully acknowledge the evaluation and organizing committees of the Iacmag for this wonderful recognition. I would also like to congratulate the other nominees on this award. And I look forward to interacting next year with the Iacmag community. I would say with a special reward for me that the location of the conference will also coincide with the place where I was trained. So I'm humbled and very proud of this award. Thank you again for this wonderful opportunity, and I look forward to seeing you in person finally next year.
Exactly. Thank you so much, Alessandro. Congratulations again to all the winners, and many thanks again for letting me be part of this amazing conference. I look forward to be with you next year and, like I said, celebrate together. Thank you.
Thank you very much, Julia, for managing this, and congratulations to all. I would like to thank also Professor Kerry Rowe and Veronique Dansereau for their presentation. And now it's time to move to the coffee break. So we will start again at 10 to 5 Central European time, but let's say we can do it at 5 to 5 Central European time. So let's take 5 additional minutes on the program, because I'm sure you will enjoy the coffee break. So I invite you to move. You have to go to your portal and go into the coffee break and find out what you can do there. It's a way to interact. See you in less than 10 minutes.